Welcome students for lecture number 2 of work power, energy and batteries of unit number 6. In my previous video lecture, I have completed effect of temperature on resistance, resistance temperature coefficient, insulation resistance and numerical based on RTC and insulation resistance. In today's lecture, I am going to cover conversion of energy, electrical system, mechanical system and the thermal system. So let us start with the electrical system. In electrical system, what is work done? So work is said to be done when a charge is transferred from one point to the other through a potential difference. So work done is equal to charge into potential difference. Now charge in terms of current and time, that is current is charge per unit time, hence charge is equal to I into T. So W equal to I into T into V. I is the current, T is the time for transferring the charge and V is the voltage. If I write current in terms of resistance, then W is equal to V square upon R into T. If I write voltage in terms of current, then the equation becomes I square RT. So W is equal to I into T into V or I square RT or V square upon R into T. This is the electrical work done. Next is power. Power is the rate of doing work, which is equal to work done upon time. So work done is V into I into T divided by T. So power is V into I. Again we can write V and I in terms of resistance, so I square R, or it is V square upon R. Power is measured in watt. If you consider the formula, power is equal to work done upon time. The work done measured in joules, time in seconds, so watt is equivalent to joule per seconds. So 1 watt is equal to 1 joules per second. Energy. Energy is nothing but the capacity to do work, which is it is nothing but the work done is always taken as a measure of the energy used. Hence the energy expended is equal to work done electrically, which is equal to V into I into T. This is the energy. That means energy and work done is the same thing. Energy consumed by an electrical circuit is said to be 1 watt second when it utilizes the power of 1 watt for 1 second. That means if you want to find out energy consumed by an electrical circuit, then energy consumption is equal to power into time. So if you utilizes 1 watt power for 1 second, then energy consumption is 1 watt seconds, which is equivalent to joules. So 1 joule is equal to 1 watt seconds. Now the commercial unit of electrical energy, which is also known as board of trade, is kilowatt hour. Now we are converting this kilowatt hour into joules because every time we are expressing energy in terms of joules. So for conversion purpose, first we have to use this conversion, that 1 joule is equal to 1 watt seconds. So convert 1 kilowatt hour into watt seconds. Converting kilowatt into watt, that is 1000 watt hour. Then converting hours into seconds, so 1000 into 3600. So it is equal to 36 into 10 raised to 5 watt seconds or joules. This 1 kilowatt hour is equal to 1 unit. So commercial unit of energy is kilowatt hour. So how to find out the cost of electricity? For that, first what you have to do, find out the energy consumed in kilowatt hour. So energy consumed in kilowatt hour is equal to power in kilowatt into time in hours. Then the total cost is equal to energy consumed in kilowatt hour into cost per unit into number of days. So by using this formula, we can easily find out the electricity bill. Sometimes in the numericals, the power is given in terms of, energy is given in terms of units. 1 kilowatt hour is equal to 1 unit. Next is the mechanical system, quantities and units. So the first quantity is, basic quantity is mass, matter possessed by a body, which is measured in kg. Velocity, distance per unit time, which is measured in meter per second. Acceleration, rate of change of velocity, meter per second square. Force, mass into acceleration, it is measured in Newton. Weight, mass into gravitational force, the value of G is 9.81 meter per second square. Then what is torque? It is the product of force and a perpendicular distance from the line of action of force to the axis of rotation. Means what is R? R is nothing but radial distance of motion. So torque is equal to F into R Newton meter. Newton meter is its unit. Then mechanical work done. Work is said to be done on a body when a force acts on it and the body moves through some distance. So mechanical work done is equal to force into distance. It is also measured in joules. The work done is 1 joule if a force of 1 Newton moves the body through 1 meter in the direction of force. Next is mechanical power. Power is again the rate of doing work. So power is equal to work done upon time. So in this formula, work done is the mechanical work done, that is force into distance divided by time. Unit is joules per second or watt. Energy. Energy is defined as the capacity to do the work. The work done is stored in the body in the form of energy. Hence work and energy are measured in the same unit, that is joules. So in mechanical system there are two forms of energy. One is known as kinetic energy, the energy which is possessed by a body due to its motion. So kinetic energy is equal to half mv square. Potential energy, it is the energy possessed by a body due to its position. So potential energy is equal to mass into gravitational force into height. Its unit is joules. Next is the relation between torque and mechanical power. So for this, here I am considering a pulley whose radius is capital R. Now the force is applied to the pulley, and due to this force, this pulley is rotating with n revolutions per minute. That means in 1 minute, pulley is taking n revolutions. So this capital N is nothing but the speed of the pulley in revolutions per minute. Now what is torque? Torque is nothing but the force into radial distance. So here the radial distance is the radius of the pulley. So torque is equal to force into radius of the pulley. Now we have to find out work done in 1 revolution. So mechanical work done is force into displacement or distance. So in this case, force into the distance covered by pulley in 1 revolution. So in this case, the distance covered in 1 revolution by the pulley is nothing but the circumference of the pulley. So the distance is equal to 2 pi r. So the work done in 1 revolution is equal to 2 pi r into force. Now we have to find out the time required for pulley to complete 1 revolution. Now for n revolution, the time is 1 minute, that is 60 seconds. So for 1 revolution, what is the time? That is 60 upon n. So power is equal to 2 pi n by 60 into F into R. Now this 2 pi n by 60 is nothing but angular velocity and F into R is nothing but the torque. So power, mechanical power is equal to torque into omega, where omega is the angular velocity, that is 2 pi n by 60. It is measured in radian per second. Suppose if this capital N, that is speed, is given in RPS, then the omega is simply 2 pi n. Now the next system, that is the thermal system. In thermal system is related to heat energy, or it is related to heat. So consider the thermal heat energy. The flow of current through a material produces a heat according to principle of conservation of energy. The heat energy spent must be equal to the heat energy produced. So this is also known as Joule's law. So by the Joule's law, heat energy is equal to, now the current is flowing through a certain material for the certain time and some voltage is applied. So what is the heat energy? Heat energy is equal to V into I into T. Again I am writing here current. In terms of current, it is I square RT. In terms of voltage, it is V square upon R into T. Then specific heat capacity, the quantity of heat required to change the temperature of 1 kg of a substance through 1 degree Kelvin. So specific heat capacity can be denoted by C. C is equal to Q upon M into delta T. Now Q is the heat produced, M is the mass, and delta T is T2 minus T1. So the unit is joules per kg K. The next type of heat energy is sensible heat. It is the quantity of heat gained or lost when change in temperature occurs. It is called as sensible heat. That means whenever there is only change in the temperature, there is no change in the state, then it is known as sensible heat. For example, you are just changing the voltage. Lukewarm water is the example of sensible heat, because in that we are just increasing the temperature of the water. We are not changing its state. So sensible heat is equal to mass into specific heat capacity C into change in temperature, that is T2 minus T1. It is energy or heat. This is related to heat energy, so its unit is joules. Now the unit of heat is normally the unit of heat is calories. That the definition of calorie is, it is the amount of heat required to raise the temperature of 1 gram of water by 1 degree centigrade. Since it is a form of energy, so it can also be measured in joules, because while solving the numericals we are considering the heat energy in joules. So here some relations are very important. That relations are 1 calorie is equal to 4.186 joules, 1 joule is equal to 0.2389 calories, and 1 kilowatt hour is equal to 860 kilocalorie. Now for this conversion, 1 kilowatt hour is equal to 860 kilocalorie, we have to use the conversion of joules. That is 1 kilowatt hour is equal to 36 into 10 raised to 5 joules, and 1 joule is equal to 0.2389 calories. So by using that relation, we will get the value as 860 kilocalorie. You just verify that. Then specific latent heat. Now in specific latent heat, in this particular heat, the quantity of heat required to change the state of the substance, that is solid to liquid or liquid to gas, without change in its temperature, it is called as latent heat. That means if you are changing the state of the substance, then the heat is latent heat. For example, when a body is heated beyond its melting point, its solid state gets converted into liquid state. During this conversion, temperature of the body remains at its melting point. Okay, so this is now in which there is a change in the state of the substance takes place, then in that system consider the specific latent heat. Heat required to convert a body from solid to liquid state at a constant temperature is known as specific latent heat of fusion or liquefaction, and if it is changing from liquid to gas, then it is known as vaporization. Now for finding specific latent heat, m is given as a mass of the body, L is the specific latent heat of a material. It is in joules per kg. This specific latent heat is also known as specific enthalpy. It is the heat required to change the state of 1 kilogram mass of a substance without change in its temperature, and hence its unit is joules per kg. So the total heat is equal to mass into specific latent heat. Next is calorific value. Heat energy can be produced by burning the fuels. The calorific value of a fuel is defined as the amount of heat produced by completely burning unit mass of that fuel. So it is equal to mass in kg into calorific value. So calorific value is also measured in kilojoules per gram or kilojoules per kg. Now the three systems are quantities of all the three systems are completed. Now the conversion of this systems, that is energy conversions from one form to another form. So energy can neither be created nor be destroyed, but it can be converted from one form to another form. And while converting from one form to another form, some of the energy is lost as a heat. So here are some examples in which the conversion of energy takes place. Electric motor. Now in electric motor, we are giving supply at the input and we are getting some work done at the output. That means electric motor is the example of electrical to mechanical energy conversion. Then water pump. It is in case of water pump, again the pump motor is driven by electrical supply. So input is electrical and output is we are getting water from certain heights. So output is mechanical, which is nothing but the potential energy. Okay, so these are some examples. So for any system, there should be one input energy and output energy. So the efficiency can be defined as the ratio of energy output to energy input is known as efficiency. It can also be expressed as ratio of power output to power input. You have to find out efficiency in terms of energies or power, but input and output should be same. Means if you are using in terms of power, then output power upon input power. If you are using in terms of energy, then it is output energy upon input energy. Its value is always less than 1. Higher its value, more the efficient is the system of the equipment. So its symbol is eta. So eta percentage efficiency is equal to energy output upon energy input into 100 or power output upon power input into 100. Now these are some systems in which the conversion of energies can be takes place. So example is motor pump set or a crane in which electrical energy is converted into mechanical energy, that is the potential energy. In hydropower plant, again the input is the potential energy of water which is stored in the dam, that means the mechanical energy, and the power can be generated, so the output is electrical energy. Now this system is thermal to electrical. So diesel generator set in which diesel is used as a fuel and the burning of fuel produces the heat energy, that is the thermal energy, which is converted into electrical energy. So output is electrical. Then electrical to thermal, the examples are electric heaters, boilers, furnace, kettles. So in which input is electrical and output is thermal. that is the thermal energy. So these are the energy conversions. Now just this is the revision of formulas of mechanical system. You just go through it before solving the problems. So force is mass into acceleration, weight is mass into gravitational force, torque is force into r is the radial distance, work done is equal to force into displacement. Energies are two types of energies, kinetic energy half mv square, potential energy mgh, power is equal to work done upon time. Then power is equal to torque into angular velocity. This power is mechanical power. Then angular velocity is equal to 2 pi n upon 60 radian per second, where n the speed in revolutions per minute. If the speed is given in revolution per second, then omega is 2 pi n radian per second. So while solving the numericals, this is very important, whether the n is given in revolution per minute or it is in revolution per second. Okay, now consider the examples. In a house, various electrical appliances are put onto the supply. As per the following schedule, during a day, we have to estimate the bill for consumption of electrical energy in this house for a month of 30 days at a rate of rupees 2.5 per unit. In short, you have to find out electricity bill for a 1 month. Okay, so what is the steps? The first step is, first you have to find out how many loads, that means the quantities of appliances. Then you convert that quantities power of that appliances into kilowatt. So let us say here the first load is 4 fluorescent tubes, each of 40 watt for 6 hours. Okay, so here the 4 fluorescent tubes we are considering, and its kilowatt rating we are converted into kilowatt, and the number of hours are 6. So find out the total energy consumption for per day. Then one electric geyser whose rating is given in kilowatt only, so 3 kilowatt hour. Iron 750 watt converted into kilowatt. Again the time is given in minutes, so convert into hours. So this is the answer. And then other miscellaneous electrical load of 400 watt for 3.5 hours. So adding all this kilowatt hour, 5.86 kilowatt hour is the energy consumption for 1 day for this house. Now what we have to find out? We have to find out the total cost of electricity for a complete 1 month. Okay, and here the rate is given as 2.50 per unit. Per unit is equivalent to 1 kilowatt hour. Means for 1 kilowatt hour energy consumption, the cost is 2.50 rupees. So the formula is, first we have to calculate energy consumed for a month, that is 30 days of month is given here. So this is the total energy consumption for complete month, and the cost is equal to, that means this much minutes, cost per 1 minute is 2.5, hence the total units are 175.8. so the answer is 439.50. Now the next example, a belt driven pulley of 0.4 meter in diameter rotates at a speed of 4 revolutions per second. Diameter of the pulley is given 0.4 meter and the speed, that is capital N, is given in revolutions per second, that is in RPS. Here the speed is given in RPS. Then the tension in the tight side of the belt is given as 420 Newton and the slack side is given as 80 Newton. So we have to find out the torque on the pulley and the power developed by the pulley. Now this is a pulley, this is a mechanical load, so here we have to consider the mechanical power. So first we have to calculate the torque is equal to force into the radial distance, that is in this case the radius of the pulley. Now for finding the force we have to first find out the net tension in the pulley. So that net tension is nothing but the force T1 minus T2, that is tension on in the tight side minus tension in the slack side. So here the value of torque is 68 Newton meter. Now find out the value of omega. Now here n is given in RPS, so omega is equal to 2 pi n. Then the mechanical power is equal to torque into omega. Now consider an electric furnace is used in order to melt 50 kg of tin per hour. So the mass of the tin is 50 kg and for melting it required time is 1 hour. 1 hour we have to convert it into seconds, so 3600 seconds. Melting temperature of tin is given, that is T2 is given 235 degrees centigrade and room temperature is given 15 degrees centigrade. So room temperature means T1 is equal to 15 degrees centigrade. Then latent heat of fusion for tin is given 13.31 kilocalorie per kg. Now it is given in per kg, so this is specific latent heat. Specific heat of tin is 0.055 kilocalorie per kg K. Means specific heat means C is given. Then if the input to the furnace is 5 kilowatt, find the efficiency of the furnace. Okay, now this furnace is electric furnace, so its input is electrical and output is thermal, because here you are melting the tin, so heat will be produced. But input to the furnace is 5 kilowatt is given, so it is in kilowatt, that means the input power is given for the furnace. Okay, so first what we have to do, we have to just first find out what is the output energy for the electric furnace. Now the output energy for the electric furnace, tin is melting, that means there is a change of state of a substance. That means the two types of heat produced, one is known as sensible heat for changing the temperature of the tin, plus for changing the state of the substance, that is the latent heat. Hence the total heat energy produced, that is the output energy, is equal to specific heat plus latent heat. Because in this example where tin is melting, that means it is changing its state. So here the two types of energy is considered as sensible plus latent heat. Then convert these energies into joules. Then find out in terms of power, that is power is equal to output energy upon time. Now the time required for melting the tin is 1 hour, so converting into seconds, so this is the output power. Now input power is already given, so efficiency is output power upon input power into 100. Now consider an electric pump lifts 12 meter cube of water per minute to a height of 15 meter. So the mass of the water is given as 12 meter cube. Now the conversion here is 1 meter cube is equal to 1000 kg. Hence the mass of the water is 12 into 1000 kg. Then the time required is T is equal to 1 minute is given. So 1 minute time, which is equal to 60 seconds. Then the height is given 15 meter. Its overall efficiency is also given as a 60%. Find the input power. If the pump is used for 4 hours a day, find the daily cost of energy at rupees 2.25 per unit. So in the first case, what we have to find out? We have to find out the input power. Now in this problem, electric pump is there, so you should know what is the input power and what is the output power. Electric pump, so input power should be electrical, and output power, here we are using pump for lifting a water, that means we are lifting a load from certain height. So energy which takes place here is the potential energy, that is the mechanical energy. So output is mechanical, that is potential energy, m into g into h. And while calculating the mass, the care should be taken, convert meter cube into kg. Conversion is 1 meter cube is equal to 1000 kg. So find out the energy output. Now the efficiency is known, output power is known. So by using the efficiency formula, energy input is equal to output upon efficiency. So this is the input energy of a system. Now what you have to find out? You have to find out power. So power is what? Power is energy upon time, and the time required for lifting the water is 1 minute. So convert into seconds. So input power is equal to input energy upon time. Then in the next case, if the pump is used for 4 hours a day, find the daily cost of energy at rupees 2.25 per unit. That means we have to find out the bill, electricity bill of pump for 1 day. So cost is equal to, first what you have to find out? You have to find out first the energy consumed. Energy consumed find out कैसे करेंगे? Input power is 49.05 kilowatt. So energy consumption is equal to power in kilowatt into time in hours. So 49.05 into 4. Okay, and cost is equal to energy consumption into unit per cost, that is 2.25. Next problem. The effective head of 100 megawatt power station is 220 meter. 100 megawatt power station means here the output power is electrical, which is given as 100 megawatt. Mega means 10 raised to 6 watt. So 100 into 10 raised to 6 watt. Then power effective head means the height. See here, the generator is here and the turbine is shown here. That turbine is coupled with the generator, and this total head is 220 meter. Station supplies full load for 12 hours a day. So the load is supplied by the station is 12 hours. The overall efficiency of a power station is 86.4%. Find the volume of a water used. Now in this is the case of hydro power station. So in hydro power station, what is the input power? Input power is potential energy and output power is electrical energy. Okay, so if you find out the potential energy, then you will get the value of mass of the water. Okay, so first we have to find out energy output for a full load. Here 100 megawatt power is given into hours per day, 12 hours per day. So the energy output for energy is equal to 1200 into 10 raised to 6 watt hour, and convert this energy into joules. 1 kilowatt hour is equal to 36 into 10 raised to 5 joules. Use that relation. Then input energy, we got the input energy as 5 into 10 raised to 12 joules. Now potential energy is nothing but the input energy supplied. So here we got the value of mass in kg, but volume, it is in terms of volume, so we have to convert it into meter cube. So again the relation is 1 meter cube is equal to 1000 kg, hence the volume is 2.3167 into 10 raised to 9 divided by 1000 meter cube. Now another type, an electric furnace is used to melt aluminium. Initial temperature of solid aluminium is 32 degrees centigrade. Initial temperature means T1, and its melting point is given as T2 680 degree centigrade. Specific heat capacity of aluminium, that is C, is given 0.95 kilojoules per kg K, and the heat required to melt 1 kg of aluminium at its melting point is 450 kilojoules. If the input power drawn by the furnace is 20 kilowatt and its overall efficiency is 60%, find the mass of aluminium melted per hour. So here input power of the electric furnace is given 20 kilowatt and efficiency is also given 0.6%. Here one more thing is given, that is 450 kilojoules, that is the heat required to melt 1 kg of aluminium. Melting takes place means the heat produces latent heat. So first what we have to find out? We have to find out the total heat, sensible plus latent heat, and this 450 kilojoules for 1 kg, that means this is the specific latent heat, that is mass into L. L is 450 kilojoules. So total heat is sensible heat plus latent heat. Then the total output energy, M is not given, we have to find out the value of M. Okay, then time is equal to 1 hour as a mass of aluminium per hour to be obtained. So input energy is equal to power input into time. Time required is 1 hour, so energy is equal to power into time. So here we are getting the value in terms of energy. Then output energy is input upon efficiency. Here we got the value of output energy. Now put this output energy in this equation, find out mass of a aluminium per hour will be melted. Now the next type, this is based on calorific value. In a thermal generating station, the heat energy obtained by burning 1 kg of coal is 16,000 kilojoules. Now this 16,000 kilojoules is nothing but the calorific value, because what is the definition of calorific value? It is the energy required to burn 1 kg mass of a coal. So this 16,000 kilojoules is the calorific value. Find the mass of a coal required to get an output electrical energy of 1 kilowatt hour from the station. Now this output is electrical energy, 1 kilowatt hour is given, and its efficiency is also given, that is 80%. Now this is a thermal generating station, and that means the input is thermal energy and output is electrical energy. Again this energy is related to calorific value, so input energy is mass into calorific value. So here in total input energy is equal to mass into calorific value. Now output of the electrical energy is given 1 kilowatt hour. So you convert this into joules by using the relation that 1 kilowatt hour is equal to 36 into 10 raised to 5 joules. So input energy is equal to output energy in joules divided by efficiency. So here we got the value of input energy. Now put that value in this equation. So mass for the coal required is 1.25 kg. Now this is the another type of problem. This is based on mechanical system. Okay, calculate the current required by 1500 volt DC locomotive when driving a total load of 100 into 10 raised to 3 kg at 25 km per hour up on incline of 1 in 100. Now this is the example of electric locomotive, that is battery operated vehicle. So for that current is given as 1500 volt DC. Then the total load in the locomotive is 100 into 10 raised to 3 kg, and the speed of the locomotive is given as 25 km per hour up on incline of 1 in 100. The locomotive is moving on the inclined plane. So assume tractive resistance of 0.069 Newton per kg. Now this tractive resistance is given. Tractive resistance is nothing but the frictional resistance is given, and efficiency of motor and gearing is 70%. Okay. Now here the inclination is given for finding the angle of curve. Okay, so here the angle is equal to, if you find out angle, the angle is very small. So when the angle is very small, then that time sin theta is equal to tan theta, hence the value is 0.01. Now consider this case. Now this vehicle is going upside, so its weight, it is inclined plane, so the weight has two components. One is W cos theta, vertical component, and horizontal component is W sin theta. Now in this particular case, if you want to find out the work done for this vehicle, so work done is equal to force into distance traveled. Okay, that is the work done by the vehicle. So for finding the force, we have to consider the opposing force of the vehicle. So here W sin theta and the tractive resistance, that is the frictional resistance between wheels and the road, is opposing the motion of the locomotive. Hence the resistance force is equal to, total force is equal to the horizontal component of weight, that is W sin theta, plus the tractive resistance of total load. Here tractive resistance of per kg is given. So you first calculate for the total load, that is 0.069 into 100 into 10 raised to 3. So this is the tractive resistance for the total load. So total resistance, that is nothing but the force, is equal to 16710. Now the speed is given in kilometer per hour. So convert that into meter per seconds. Okay. So speed is so D is equal to 6.944. So work done is equal to, here we are getting the value. Then output power is work done upon time. Time required is 1 second. So this is the output power. Then efficient input power is output power upon efficiency. So here we are getting the input power. Now this is a DC locomotive, electrically driven locomotive. So its input is obviously electrical. So electrical power P in is equal to V into I. So the current is 110.5151 ampere. Now this example is again of the thermal system. An immersion heater supplied at 250 volt DC is placed in a bucket containing 5 liters of water. Now immersion heater means again the input power is electrical and the water is heating, so the output is thermal. Temperature goes up to 50 degrees centigrade in 20 minutes. Now here there is only change in the temperature, so the heat takes place in this particular application is sensible heat. The water equivalent of the bucket is 500 grams. Okay, now this example is a bit different. Here the water equivalent of the bucket is given. So when the water equivalent of the bucket is given, that time what we have to do, we have to add this with the weight of the water, because we are considering the heat wasted for heating the container. Hence the output, the total mass will be the mass of a water plus water equivalent of the container. Then heater, calculate the heater resistance. Specific heat of water C is given 4180 joules per kg K, and heat loss due to radiation is negligible, means we have radiations losses are neglected. Now voltage is given. First we have to calculate sensible heat, that is the thermal energy, output energy. Mass is mass of a water plus water equivalent of a bucket into specific heat capacity into change in temperature. Then find out the input power, which is the electrical power. After getting the electrical power, power is equal to, here the voltage and voltage is given. Here we got the value of power. Find out the resistance. So write the power in terms of V square upon R. Find out the value of, we got the value of R here. Again this is the example of electric furnace. So here input is electrical and output is thermal. Here again the melting of tin is takes place. So here we have to consider sensible heat plus latent heat. This example is similar example. then you find out output power and then find out efficiency. This is for practice. Then this is the another system. A boiler steam turbine generator system consumes 1000 tons of coal and generates 2000 megawatt hour energy in a day. The calorific value of the coal is 30 megajoules per kg. Find overall efficiency of the system. Now this system is steam turbine is coupled with the generator. So here also the thermal energy is input energy. Generator is generating electricity. So the output is electrical, which is given as 2000 megawatt hour. Calorific value of the coal is given 30 megajoules per kg. Mass is given 1000 tons. So here first we have to find out input of the system. So input of the system, here the fuel is coal is given, that means the input is mass into calorific value. So mass is given as 1000 tons, convert into kg. So here the value of input to the system we got. Then the overall efficiency is output upon input. Now this is the system again, electrical to mechanical. But difference is here different efficiencies are given. A pump driven by an electric motor lifts 10 meter cube of water to a height of 30 meter in 5 minutes. Efficiency of the motor and pump and the motor are 72.5% and 90% respectively. Calculate power input to the motor and the energy consumed by motor if it works for 4 hours. So here the efficiency of motor and pump are given separately. So first what we have to do, we have to first find out the overall efficiency of a system. So the overall efficiency of a system is efficiency of a motor into efficiency of a pump. Now in this particular example, input is electrical and output is potential energy. So output power is equal to output power is equal to output energy upon time. So here output energy is equal to M into G into H. So here is the output power. Then input power is equal to output power upon efficiency, and here we are considering the here is the printing mistake. So here is the efficiency, that is the overall efficiency 0.725 into 0.9. So this is the input power. Then power consumption in hours equal to power in kilowatt into time in hours. Now here is the same example. It is again the same example from electrical to mechanical, and mechanical energy is potential energy. Again the motor and gear efficiencies are given separately. So here we have to find out gear and motor efficiency, that is overall efficiency 0.85 into 0.6. So input energy is equal to output energy upon overall efficiency. Output energy is mechanical, that is potential energy mg into h. And from after getting the value of input energy is electrical energy. So you convert that energy into joules and then find out the input current. Then this is the same example like a electric locomotive. Here what we have to find out, an electric motor is driving a train weighing 100,000 kilograms upon an inclined track of 1 in 100 at a speed of 60 km per hour. The frictional force of tracks is 10 kg per 1000 kg of its weight. If the motor operates on 11 kV, find the current taken by the motor, assuming the overall efficiency of the system is 70%. Now this is the same example. Here also we have to consider first we have to find out mechanical work done, that is the mechanical energy, which is the total opposing force into distance. So first we have to find out the force trying to pull the train downward is W sin theta. Then frictional force we have to find out. Frictional force is also given 10 kg per 1000 kg of its weight, converting into Newton. Then this is the total opposing force. Then here the speed is given as 60 km per hour. So we are converting into meter per seconds. Then the output power is equal to force into distance upon seconds, because it is force into distance is work done upon time. And input power is output power of an efficiency, and then you find out the value of current. Now this is the example of calorific value. I have already explained it, so you just go through it. Now this is the example of pump motor. Here also overall efficiency is given, and you have to find out first output energy, then you find out input energy, and then you find out input power. After getting the input power, find out the energy consumption, and then you find out the total cost. The effective head of 100 megawatt power station is 220 meter. Station supplies full load for 12 hours a day. The overall efficiency of power station is 86.4%. Then find the volume of the water used. So here all the numericals based on thermal, electrical and mechanical systems are completed. Now you go through these numericals, do the calculations on the calculators and practice it. Thank you.